Starting off with the first question, figure 6.1 shows a metal bar placed inside a vertical solenoid. Alright, so solenoid is when you have a coil, when you have a wire, straight wire, and you wound it in the form of a coil, just like a spring. And preferably, we wound it over a metal bar, generally on an iron core. A solenoid is a coil of several turns of insulated wire. The DC power supply is connected to the solenoid so that there is current in it. When the supply is switched on, the metal bar is a short distance above a small pile of iron clips in a glass dish. The power supply is switched on, left on for several seconds, then switched off. Describe the behavior of the paper clips when this procedure is carried out using a bar of aluminum. So for this one, you have to recall the magnetic and the non-magnetic materials. And for the syllabus of O-level physics, like I said, when we refer to magnetic materials, we refer to ferromagnetic materials, the materials which are attracted by the magnets. So these are the only magnetic materials that we refer to. Aluminum we studied is not a magnetic material. So even if you switch on the power supply, the current would start flowing through the solenoid. The solenoid would be magnetized. It would create the magnetic field, but that magnetic field would be having no effect if the metal bar is made up of aluminum. But even if the current is flowing, aluminum is non-magnetic material, so magnetic field would not pass through the aluminum. So what happens to the paper clips when the metal that you have used is aluminum? The paper clips remain stationary. Alright, then you have the next one. The metal bar in this case is made up of iron. So as soon as you switch it on, your iron bar gets magnetized. Magnetic field would be penetrated through the iron core. It would be magnetized and it would attract the paper clips towards it. And when the switch is left on for several seconds, the paper clips are still attracted towards the metal bar. And for the third point, when you switch it off, the magnetic field in the iron bar vanishes and it would be demagnetized and the paper clips would fall down. Because iron is a soft magnetic material, it magnetizes quickly, but at the same time it demagnetizes quickly as well. So what we write is paper clips are lifted up to the rod and when switched off, when the circuit is switched off, they fall down Reason? Because it is soft magnetic material. It magnetizes quickly. Soon as you switch it on, it gets magnetized. Soon as you switch it off, it gets demagnetized. Then you have the third one. What happens if you have the steel, if the iron bar is made up of steel? So steel is a hard magnetic material. So what that means is when the current starts flowing through it, it would be magnetized. But if you switch it off, it would not be demagnetized quickly. So it would stay, or it would stay magnetized even if you switch it off for a while. So for the paper clips are lifted up and remain attached to the rod even if switched off. Even when circuit is switched off. Alright, so you would have seen the question on the screen. Figure 7.1 shows the structure of a circuit breaker that uses an electromagnet. The circuit breaker operates when the current is 10 amperes. On figure 7.1, mark with an arrow the force on the iron bar caused by the electromagnet, and we have it for 1 mark. On figure 7.1, mark with an arrow the force on the iron bar caused by the electromagnet. Alright, so for this one, you see, as the current flows, just take a look at the diagram. As the current flows through the electromagnet becomes magnetized. So this is what happens in the first step. As the current flows through the electromagnet becomes magnetized. Iron, being a magnetic material, is attracted towards the electromagnet, so the force would be upward. Force on the iron rod or the iron bar would be upward. We could call it represented with the letter F, even they haven't asked for it. Part B. Suggest one reason why the iron bar does not move when the current is less than 10 amperes. Basically, this is how we design a circuit breaker. It is designed to operate on 10 amperes. If the iron bar was able to move for a current less than 10 ampere, then what is the purpose of circuit breaker to begin with? There would be no purpose. The circuit breaker has to be operated when the current reaches at least 10 amperes or beyond. So we designed the circuit breaker for that special case. And how do we do that? The weight, we adjust the weight of the iron bar. So for example, the current is 5 ampere. Your electromagnet would become magnetized. There would be force acting towards the electromagnet would still be trying to attract the iron bar, but for that situation, the magnetic force is not enough to overcome the weight of the iron bar. So the attractive force is not enough to overcome the weight of the iron bar. Or you can simply also you can write here, attractive force is not enough. attractive force is not enough to overcome the weight of the iron bar. If you want to write the full sentence, when the current is greater than 10 amperes, the circuit breaker stops the current. Explain what happens in the circuit breaker when this occurs. So in this part C, they have basically asked you to explain the working of the circuit breaker. So how do we do? We have written this in sequence. We wrote down the steps when we were studying the topic of the circuit breaker. Now how do we write it over here? Let's see that. So first of all, I'm going to mention the steps. The first step is, as the current exceeds 10 ampere, let's say the current now is 12 amperes, your electromagnet becomes strongly magnetized, and the magnetic force or the attractive force of the electromagnet is large enough to attract the iron bar towards it. So iron bar moves someplace over here, and due to which, as the iron bar moves over there, these contacts are broken, or this contact is broken. And as the contact is broken, because in that case the spring would try to pull the copper bar across, and the contacts would break. As it's moved upward, the iron bar is moved upward. This is the second step. The spring would try to pull the iron bar towards it. The contact would be broken. These are the 4 stages that are involved in this working of the circuit breaker. Now we write all 4 of them. The first one, once again, electromagnet becomes magnetized. Then in the next one, it pulls the iron bar towards it. Then in the third one, the spring pulls the copper bar across. Due to which the contacts break, and so does the circuit. Alright, then we have the next one, state and explain how the electromagnet can be altered so that the circuit breaker stops the current at less than 10 amperes. So in order for that, the circuit breaker should be able to stop for a current even less than 10 ampere. What we have to do is we need to increase the magnetic force. I mean, even at a current of 8 amperes, the magnetic field should be strong enough to lift the iron bar towards it, or to pull the iron bar towards it. Or what we can do is, we don't try to change the electromagnet. What we try to do is we try to reduce the weight of the iron bar. So if the iron bar is having less weight, what's going to happen is it would be attracted, it would be pulled up even by a weaker magnetic field. So there are plenty of ways you can do that. So what I'm going to explain is in terms of the less weight of the iron bar. Pulled up by magnetic field. Produced by lesser current or lower current. Alright, so in that case the magnetic field is not strong enough, but since the iron bar is not too heavy, even that weaker magnetic force or the weaker attractive force would be able to attract the iron bar towards it. In that case, the spring would be would pull the copper bar towards it. Oh, so we had this. Yeah, sorry, the bar that is being attracted towards the electromagnet is the iron bar. Copper bar is the other one. Iron bar, and spring pulls the copper bar. Yeah, this one is actually the copper bar. So for the part C, we also have when the current is greater than 10 ampere, the circuit breaker stops. Explain what happens in the circuit breaker when this occurs. Electromagnet becomes magnetized. It attracts the iron bar towards it. The spring pulls the copper bar towards it. The contacts are broken. So first the iron bar is attracted towards the electromagnet, then the spring pulls the copper bar towards itself in order to break the circuit or to break the contacts first. That was for the second question. A magnet is placed on a bench as shown in figure 8.1a, and P of the rod of a rod is held above each end of a magnet in turn as shown in figure 8.1b and in 8.1c. One end of the magnet is lifted off the bench in both cases. The first one that we have is suggest what material the rod is made from. So I mean, it's pretty much a simple one. The rod is made up of a material which is magnetized easily. Soon as you bring the rod towards it, it gets lifted. So it must be made from a material that is able to get magnetized easily. So what we can write here is it's made up of soft iron, or simply you can write iron as well. Then we have the second one, explain how the rod lifts each end of the magnet off the bench. Now for this one, first of all, since the rod is made up of magnetic material, like we answered previously in the part 1, the rod becomes magnet. Alright, once you bring it close to the magnet that is placed on the bench, once you bring this rod close to this one that is placed on the bench, the rod also becomes a magnet, an induced magnet to be precise, because actually it was not a magnet, but it became a magnet due to influence of another magnet. So we call it induced magnet. And why are they attracting to each other? Because the rod would become magnet in such a way that it would induce a south pole over here and north pole over here, and then these two opposite poles would attract each other. So what we can write here for this one is the rod becomes an induced magnet and induces in opposite poles in front of the rod, in front of one of the end of the rod. On its end near the magnet. And opposite poles attract. And the opposite poles attract. Figure 8.2 and 8.3 show views of the wire carrying a current downward through a horizontal board. Alright, so actually if you see this thing from the top, alright, you're trying to view it from here. From the top, this thing would appear something like this. I mean, the eye should be drawn this way. Yeah. So you're trying to view from here. So the top view of this case would appear as the image 8.3. On figure 8.3, draw the magnetic field due to the current in the wire. Whenever the current flows in a straight line, the magnetic field is circular. And how do we find the direction of that circular magnetic field? The circular magnetic field can either be clockwise or counterclockwise. We use the Fleming's right hand rule, but the rule of thumb is if the current is into the paper, the magnetic field is clockwise. So we need to draw two circles, at least two circles. First one. And third one a little bit further. and the circles must be concentric, means they must be having the same center. And you have to be careful with the spacing. The spacing between the consecutive circles should be increasing, and you also have to mark the direction for the current into the paper. The direction of the magnetic field is clockwise, because your thumb has to be into the paper, and if you place your thumb into the paper, your fingers would be curling clockwise. Yeah, so once again, for the last part, the magnetic field is stronger closer to the wire. State how the magnetic field lines indicate that the field is stronger. The magnetic field lines are closer to each other. If it is representing a weaker magnetic field, the lines would be further away from each other. The consecutive lines, the spacing between the consecutive lines would increase.